Okay, so we're going to review the Sig Fig rules for multiplying, dividing, adding, and subtracting, and we're going to do that as we also kind of advance our dimensional analysis activity, your measuring activity that you did in class the other day, which involves using dimensional analysis to do unit conversions. And so looking at just the very first example, when we measured the width of the lab table, and if you think about it, right, the meter stick that you used had lines for the centimeters and it had lines for millimeters. And so centimeters and tenths of centimeters would have lines associated with them, and then you would estimate one more place value, so you would estimate hundredths of centimeters. And so one of your possible values might be 91.40 centimeters. Again, for sig figs, because of the precision of the meter stick that you used. And if we want to convert that from centimeters to miles, which is what I asked you to do, then we got to find first a conversion factor to get us closer. I don't know how many centimeters are in a mile, but I do know how many centimeters are in a meter. And so remembering from chemistry, I'm going to put centimeters on bottom and meters on top, and then put the numbers that associate with those. 1 meter is equivalent to 100 centimeters, and so I put those there. The centimeters units cancels, and I've converted from centimeters to meters. So next I'm going to convert from meters to miles. From track, I remember that a mile is about 4 times around the track, which is about 1,600 meters. If I want to be a little more precise, I could say 1,609 meters is equivalent to 1 mile. And then I just paused here and reminded students that what is the value of this thing circled in green? And it looks like it's the value of 1/100th, but in reality it's not. If you think about it, what's on top is 1 meter, and what's on bottom is 100 centimeters. And how do those compare? Well, think about this. What is 2 over 2, or 6 over 6, or pi over pi, or potato over potato? If what's on top is the same as what's on bottom, then that value is 1. And so what's in the green circle is equivalent to 1. And that's why I can get away with multiplying my original measured number by this fraction without changing its value. I'm just changing its units. So when I punch that in my calculator, I do 91.40 divided by 100 divided by 1,609, and my calculator gives me this number. And so the question is, how many sig figs do I keep, right? What do I round to? Well, remember first of all that sig figs only apply to measured numbers, and so that number in green in the middle there, those are exact numbers. That's a definition. I've defined 1 meter to be 100 centimeters. It's exactly 100 centimeters. Nobody measured that. And so the only 2 measured numbers that we're considering are 91.40 and 1,609, both of which have 4 sig figs. And as you'll recall, the rule says that when we're multiplying or dividing numbers, then we take the number that has the fewest number of sig figs, and that's how many we keep in our answer. In this case, they were the same, and so we keep 4, and so I do 0.05681 miles was the value for my 91.40 centimeters. And again, that's just reminding you that that is indeed 4 sig figs. And then again, there's the rule. When multiplying and dividing, it's a number of sig figs that matters. Whichever measured number has the least number of sig figs, that's how many you're going to keep in your final rounded answer. So what about adding and subtracting? So let's take these numbers, 7.31, 8.0, and 20. If I'm going to add those, the first thing I'm going to do is what I learned when I first learned how to add decimals, and that is I'm going to line them up. And again, we're assuming that all 3 of these numbers were measured, so the sig fig rules will apply to all of them since they were measured numbers. And then now the question I'm going to ask myself is, where is the last sig fig in each of these numbers? Well, of course, in 7.31, the last one is significant. In 8.0, the 0 is significant. But in 20, only the 2 is significant. And again, if you need to refresh your memory on how to determine which ones are significant, please do so. But now I look at those last sig figs in each of those numbers and I ask, which one is the highest place value? Where does the significance end in the highest place value? And in this case, that would of course be in the tens place because of the 20. And so that, I'm going to make myself a mark there to remind me that that's where I'm going to round to. Then I'm going to do the math like normal, do 35.31, and then I'm going to round where I drew my line. And so if I take 35.31 and I round it to the tens place, that gives me 40. And you say, well, that's weird. I mean, why is it 40? Why is it so imprecise? Well, let's think a minute. This 8.0 was not exactly 8.0, right? It was a measurement. I estimated the 0, and so its real value could have been anywhere between 7.95 and 8.04, right? Those are numbers that would have given me an estimate of 8.0. But if I look at the 20, because the 2 was actually estimated, the range there is much wider. It could have been anywhere between 15 and 24. And so because of that wide uncertainty in my 20, being anywhere from 15 to 24, that's why I can't be as precise in my answer as 35. I have to call it 40 because of that imprecise measurement of 20. All right, so again, when adding and subtracting, it's not the number of sig figs, but it's where the highest place value of the least precise measurement is. So try this one on your own. Just kind of pause the recording and work it out and see how you do. So you line them up and do the addition, and then you look at where the last sig fig in each number is, which for the 120 is in the 2, and 39.3 is the second 3, and then 15. Which of those is in the highest place value? Of course the 2 is, and so I mark my line. That's what I'm going to round to. And when I take 174.3 and I round it to the tens place, I get 170. All right, try this one. 700 plus 49. Well, of course, for 700, the significance ends in the hundreds place, and in 49, it's in the ones, and so I'm going to round to the hundreds place. But if I do 749 rounded to the nearest hundred, it's just 700. You say, well, that's crazy. Why is 700 plus 49 equal to 700? Again, it goes back to how uncertain the 700 measurement was. That thing could have been anywhere between 650 and 749. And so if it was at 650 and I added 49, I only get 699. And so because the measurement of the 700 was so imprecise, basically adding the 49 doesn't change that original number. All right, here's another one for you to practice on your own for multiplying. Of course, since these numbers are multiplied, we're going to worry about the number of sig figs. 230, when written like that, has 2 sig figs. 1.48, when written like that, has 3 sig figs. When I punch it in my calculator, I get 340.4. And because 230 only has 2 sig figs, I'm going to keep 2 sig figs, and I round it to 340. All right, here's another one to practice for adding. And here's the solution. Of course, I'm going to round it to 200. Again, because of the uncertainty in the 38, but more importantly in the 200. That's a huge range of uncertainty for the 200, and so my answer ends up being just 200 again. Now someone asked this in class, they're like, well, what if it had been 200.01? Well, now where does the significance end? It doesn't end in the 2 in 200 anymore. Now it goes all the way to the hundredths place. And so now what's the least precise measurement? Well, the highest place value where the significance ends in this case is the 8 and 38, and so I'm going to round to the nearest whole number. And so now, because my 200.01 was so much more precise this time, my final answer ends up being more precise. All right, so good review on multiplying, dividing, adding, and subtracting, and make sure you complete both sets of practice, both the dimensional analysis activity as well as the Sig Fig practice on campus.